Hey guys, welcome back. Today we're going to be talking about electrostatics. It's kind of our first step in talking about one of the coolest forces in all of nature. We've been kind of building up to this. From here on out, we're going to be dealing with some forces that in some ways are just bizarre. Something that you don't even need to be in contact with to have an interaction with. And electrical forces are kind of the first of these. Well, gravity, in a way, actually was the same thing, but we later on discovered that gravity was really a case of warped space and time, and that things were still moving in what appeared to be straight paths following inertia rules under Newton's first law. Electrostatics, though, is a little different. Electricity and its behavior, the behavior of charges and magnetism is very complex, is extremely interesting, and it leads to some almost kind of magical outcomes. As a matter of fact, magicians take advantage of it all the time. So anyways, let's go ahead and start our discussion on electrostatics. So electrostatics, the word electro, of course, meaning pertaining to electricity, but statics means stationary. So we're going to be basically looking at things that are in stationary positions relative to one another, and the electrical charges that might, electrical charges and how they might behave with respect to one another, provided they aren't moving very much, right? Very slow motion. So in fact, this is what we see here. This would be a classic electrostatic experiment where we have a central spot where we see current moving to and fro this central spot. The speed of the current is actually not all that fast in this case. I should say that the speed of the charges within the current isn't all that fast. So electricity, we kind of need to get this out of the way. That electricity, it turns out, is a garbage bag term that is used by people all the time to describe all kinds of phenomena. So it's used to describe, for example, lightning, spark when we strike a match. What holds atoms together, it turns out, is also electricity. So fundamentally, we are electrical charges all connected, one within ourselves. Ultimately, as we'll discover by the end of this lecture, the force between electrical charges is much stronger than that of gravity. As powerful as gravity is, as powerful as it is that it can make black holes and rip entire galaxies apart, I hate to say it, but electromagnetics is a much more powerful force, and it's something that we are still trying to kind of wrap our brain around. We don't actually really know what it is. You could take a positive charge and a negative charge, and for whatever reason, we don't know the reason, they don't even have to touch and they're interacting. We don't know why. That makes it so interesting in and of itself. If you figure it out, you've got a Nobel Prize for sure. All right, so electrostatics involves electrical charges, which is to say the force between them, the fields that surround them. Remember that in gravity, there were, gravitational force. We figured, remember Newton's law of universal gravity, which was force equals the gravitational constant times the product of two masses divided by the r squared, or the distance between these two squared. Called that the inverse square law. Turns out there's a similar law, almost exactly the same in structure in electrostatics, but it's a little different in its nature. The field that surrounds them, remember gravitational fields, it turns out electricity has electrical fields around them too, and their behavior in different materials. For example, electricity flows very nicely through copper wire, but not so nicely through a rubber band. So the central rule of electricity, and this is something you've got to keep in mind as you go forward, because sometimes we lose track of this, that opposite charges attract one another and like charges repel. So here we have two opposites. These are positive and positive, two negative and negative. They repel. They'll actually exert a force to move one away from it. They will accelerate away from each other. In the case of a positive and a negative, they actually attract. Now, why do we call it positive and negative? Well, because we recognize this relationship between them. A famous American scientist by the name of Benjamin Franklin, who you might have heard of, he was the preeminent statesman during the American Revolution. Prior to that, he was actually a major player in the Royal Society and was publishing papers on electromagnetism, as well as many other things. But he came up with a convention of positive and negative charges, and it stuck. It's still with us today. Let's go ahead and talk about the different charges that exist in nature in general. Now, first off, the main thing that we see are protons and electrons and neutrons. So protons are basically positive electric charges, and they repel positives but attract negatives. So this is some particle that exists. And usually in an atomic structure, we find them in the nucleus, protons anyway. Electrons, however, we find usually in some type of what we call orbital or orbit away from the nucleus out here. They're negative. They have the exact same charge as the positive, but it's just a negative sign. They're opposite signs from one another. And so they repel negatives but attract positives. And neutrons are neutral electric charges. It turns out that neutrons are, in a complicated way, a combination of a proton and electron and some other stuff going on there too. But nonetheless, the result is that you have a balancing of both charges, and therefore there is no net charge. So let's talk about some of the fundamental facts about atoms. So first off, every atom is composed of a positively charged nucleus. It has to have a positively charged nucleus. If it has a neutron, it's not a nucleus, right? It's not going to be able to hold the orbit of an electron around it. And of course, that nucleus is surrounded by negatively charged electrons, or at least it's going to be attracted to negatively charged electrons. So each of the electrons in any atom has the same quantity of negative charge and the same mass, right? So all electrons are exactly the same, is basically what we're saying here. Item number 3, protons and neutrons compose the nucleus, right? We call these nucleons. Protons are about 1,800 times more massive than electrons. Electrons have mass. They are particles, but they're very, very, very small compared to the protons. But each one carries an amount of positive charge equal to the negative charge of the electrons. In other words, the mass has nothing to do with the amount of charge. The charge is different than the amount of mass. Neutrons have slightly more mass than protons and have no net charge. Why? Because they have an electron kind of fused with them. Atoms usually have as many electrons as protons, so the atom has 0 net charge. Notice this word usually. Usually you have just as much, say in helium, you have 2 protons, you can have 2 electrons going around it. Hydrogen, 1 proton, you can have 1 electron going around it. But that's not always the case. We'll talk about the exception to the rule soon. As a matter of fact, here it is right here. Whenever you have that exception, it's called an ion. So a positive ion is where you have an atom losing 1 or more electrons, which gives the overall atom a net positive charge. And when that happens, it's called a cation. Potassium, for example, does this frequently. Hydrogen does this frequently. These things lose their electrons very easily. At least it loses at least 1. On the flip side of that are cases where there are certain atoms, such as chlorine, where the atom is able to very easily gain electrons. And what it does, it gives it a net negative charge. And that's called an anion. So think of chlorine. Chlorine is a typical anion. And there's a reason why chlorine is so dangerous, because it has that strong negative charge, and it basically, if it gets into your body, just starts ripping things apart. It's a really toxic substance. So electrons in an atom have several structures that we need to be aware of, but let's just keep it simple. First off, there's the innermost electrons and the outermost ones. The innermost ones are attracted very strongly to the oppositely charged atomic nucleus. So here we have our nucleus, and we can assume that this is kind of a model of an atom. And this would be sodium in this case. And here we have sodium having a total of 11 electrons to be balanced out. Now notice it has them in 3 separate, what we call orbitals. These ones right here, real close, are going to be really tightly held by this positively charged nucleus. These ones here in the second orbital will be also relatively strongly held by the nucleus. But this third one, the one that's out here by itself, it's pretty far out there, and quite frequently it's lost. And so sodium, as it is normally found, is usually as an ion. It usually loses that other one. It can hold those first two orbitals pretty closely. That third one is usually lost. It gives the overall sodium atom a net charge of a positive, making it a cation. All right, so we also get really neat effects from electrical forces and charges. So, for example, when we rub a comb through your hair, we see a person over here who clearly has some electrical charge going through her. Electrons transfer from your hair to the comb. We'll actually see a demonstration, or at least a couple of photos of this very thing. Your hair has a deficiency of electrons. It's positively charged. So in this case, imagine that this hair is all combed out really well. This is actually something else going on right here, but you get the idea. There's positive charges in here everywhere. And remember, positive charges are repelled. So the hair that is out here is repelled from the head. But the hairs are also repelled from one another, so it all fans out, trying to get as far away from each other as it possibly can. So you kind of get the idea. When rubbing a glass rod with silk, electrons transfer from the rod onto the silk, and the rod becomes positively charged. This is an experiment that had been done all the way back, at least to medieval times, and probably even prior to that, all the way into the Greek era. So anyway, this was also an experiment not done with just glass rods. People actually recognized that if you took fur and you rubbed it on amber, it would actually create sparks or an electric charge as well. As a matter of fact, I believe the ancient Greek word for amber is electrum, which is where we get the word electricity from. Now, what is actually going on here? We've been talking about charges moving, but we're really talking about the masses that move the charge. So in any charging process, it turns out that no electrons are created or destroyed, right? You turn on the switch on your light, electrons might be moving somewhat, but they're not being created somewhere and destroyed somewhere else. The electrons are just simply being moved around. That's all that's happening. And that's what we're saying here. Electrons are simply transferred from one material to another. Here we can actually see a flow of electrons is occurring within this sphere. And that leads us to some really neat stuff, something called Coulomb's law. Whenever you hear something as a law, you probably need to take out your pencil and paper and write it down. Unfortunately, this slide, I usually do a little summary. I didn't provide a summary on this one. So now that you're here, you're going to want to be prepared to write down the equation that you see right down here, 2/3 down. We're going to explain this here in a moment. So the relationship among electrical force, charge, and distance was discovered by Charles Coulomb in the 18th century. Charles Coulomb was a really cool guy. He was a geotechnical engineer, actually. He had an interest in being able to discover the magnitude of many of the constants, and he actually took an interest in the gravitational constant, which in his time, even though Newton had discovered that there was a gravitational constant in the universal law of gravity, he didn't actually know what the value was. That was something that was not discovered until an apparatus was worked out, or actually invented, by Charles Coulomb. Charles Coulomb actually started using a couple of metal spheres, and what he was trying to do was he was charging them up, and he was looking at how much force was exerted on these two spheres. And this torsion balance, as it was called, was later used to be able to solve for the gravitational constant, but also for the relationship between the force in charged particles. So what was it that he found out? Well, his law found that that for a pair of charged objects that are much smaller than the distance between them, in other words, think of them as like point charges, like an electron, right? You have an electron a meter away from another electron. The force between them varies directly as the product of their charges. So in other words, you take their two charges and you multiply them together. And inversely as the square of the separation of distance. Wait a minute, that's inverse square law. That's just like gravity. Remember, gravity was, the force between them was the product of the masses divided by the square of the distance. In this case, it's the product of the charge. If the charges are alike in sign, the force is repelling. If the charges are not alike, the force is attractive. So in equation form, we would just say this, that the force, and this would, you could call this F, notice force is always a vector, equals K. Now K is this number, it's called Coulomb's constant. K we give the value for right here. This was actually discovered a little later on. But anyways, here's Coulomb's constant. And sure enough, here we have Q1, Q2. Now Q1 and Q2 are the charge values, right? It's some amount of charge. We haven't actually given the units for what charge is. We've just simply said there's charge. divided by radius squared. Now notice that the radius, or the distance, the radial distance between something is always a vector. Of course it's always a vector because it's a direction and it's a distance, especially in electromagnetics. But we'll keep this as it is, right? You know this, the final solution for this will always be in newtons, so we know that this Q and this Q is going to be in something called coulombs. Hey, pretty imaginative name for this. The guy came up with the equation, so he gets the unit of charge named after him, of course. And so this thing is called a coulomb, and sure enough, it also appears in the constant, 8.99 times 10 to the ninth Newton meters squared divided by coulombs squared. All right, so here we have the units for the constant. Here's the value of the constant. By the way, this is usually actually rounded to 9.00 times 10 to the ninth, or just 9 times 10 to the ninth. But 8.99 times 10 to the ninth is good. And this value actually holds really well in all substances in a vacuum. If you're going to have be measuring things that aren't in a vacuum, for example, if I have two charges and they're not suspended in space or they're not in a vacuum, let's say I put a glass wall between them or a metal plate or something like that, the value for K changes. But we're not going to get into that. Just be aware that as you get into electromagnetics, those of you that have an interest in physics and wind up studying some more of it or take a more advanced course in it, you'll realize that there's some complexity in here that makes actually electromagnetics really interesting. Things like electrical conducting, semiconductors and things like this suddenly become possible. We'll be talking about them a little later on in the class. Unit of charge is the Coulomb. Okay, we already talked about. Similar to Newton's law of gravitation for masses, underlies the bonding forces between molecules. If it wasn't for electromagnetic force, we wouldn't exist. Atoms wouldn't hold together, and atoms wouldn't bond with one another, right? So charge is really a big deal. Now, again, we're coming back to that idea. What is charge? Who knows? We still don't know what it is. It's the same question that actually Newton had on gravity. What was gravity? He just knew that he could describe the forces and how it behaved, but he actually didn't know what it was. It was actually found it very dissatisfying. Einstein came along and said, hey, it's a warping of space-time. And somebody said, well, what is that? And he said, yeah, it's pretty dissatisfying. So we still have a long way to push this frontier in science, but you get the idea. That there's a lot of really cool stuff going on. Ultimately, there's just so many questions fundamentally about what these forces are. We just take it for granted that they exist. Again, there's a Nobel Prize waiting for you if you're able to kind of connect all of these things together. All right, so suddenly things become pretty cool. We can do some neat stuff. We can do something called charge polarization. So in charge polarization, you have an atom or a molecule in which the charges are aligned with a slight excess of positive charge on one side, a slight excess of negative charge on the other. So this would be a polarized item here, right? Here it's negative on one side, it's positive on the other side. So for example, if you rub an inflated balloon on your hair, we've all done this, you grab a balloon, you rub it on your hair or on the carpet or something like that, and then place the balloon on the wall. It'll stick. And the balloon sticks to the wall due to the charge polarization in the atoms or molecules of the wall. So this is kind of a good example of this. Imagine this is a ball here and this is a wall. So this is kind of a cross-section of a wall or a beam. Here's a ball, and the ball has a positive charge, right? You rubbed it on your head or you rubbed it on the thing, you put it on a string and hung it from the ceiling, and it's going to swing towards the wall. And what is it going to do as it swings towards the wall? It's going to pull the positive charges towards it. It's going to push it's going to pull the negative charges towards it and push the positive charges away from it. And the result is polarization. So we can see that the wall will become polarized as well as the balloon will still have its positive charge. And over time, these charges will bleed back and forth and eventually the balloon will fall off the wall. It'll lose that charge polarization that causes them to attract. So let's bring in a couple of vocabulary words. We've actually mentioned them previously when we were talking about substances in earlier lectures, but let's go ahead and bring them back. Something called a conductor and an insulator. We're actually talking about, I believe, heat and heat transfer when we're talking about conductors and insulators. They're back. So a conductor, remember, is just materials in which one or more of the electrons in the outer shell of its atoms are not anchored to the nuclei of particular atoms, but are free to wander around the material. So basically, what it's saying is that remember we were talking about the sodium earlier. That outer electron is so loosely held that it can just wander around. It's not actually tied to a single atom. It's actually more of a loose conglomeration of atoms within a substance that has the ability to move freely within the lattice. So an example of this are metals such as copper and aluminum. In fact, these are called metal bonds or metallic bonds. Kind of their antithesis are insulators. These are where, in fact, the materials in which the electrons are tightly bound. They're not allowed to wander around, and they belong to particular atoms and are not free to wander about among the other atoms in the material. So, if it's attached to an atom, it's attached to that atom. It's not allowed to go and jump to another atom, at least not very easily, making them flow. So, for example, rubber and glass. Rubber and glass have this capacity. So here we see, this is exactly why we put our wires the way that we do. We put a conductor here in the middle, and then which is where our electricity will flow, or our electrical current will flow. And on the outside, we have an insulator through which it won't. Right? The materials will not move through them. So we have loosely held electrons, tightly held electrons. All right? We're going to come into why that's important here in several slides. Yeah, so bear with us. All right, so another kind of neat thing that we should talk about are semiconductors. Semiconductors are a material that can be made to behave sometimes like an insulator and sometimes as a conductor. It's one or the other depending on the conditions you put on it. And this is great for computers. You want a computer that isn't just constantly shining power through it or electricity through it. You want it to shut off or turn on under certain conditions. And they fall in the middle range of electrical resistivity between insulators and conductors. They're kind of hybrids. They can act as an insulator sometimes. They can act as a resistor or an insulator, if you will. They're insulators when they are in their pure state. And they are conductors when they have impurities. Now, this is what's really cool. Semiconductors can conduct light or can conduct electricity when light shines on it. So if a charged selenium plate is exposed to a pattern of light, the charge will leak away only from the areas exposed to light. How interesting is that? We haven't actually talked about what light is and what it's doing. But essentially what's happening is the light has the ability to dislodge the electrical or the electrons in a selenium plate. But if it's dark, they can't do that, and it acts like that's right, insulator. So this is useful for circuit boards. Superconductors are quite the opposite, actually, from semiconductors, and a lot of people in the public think they're one and the same. They're completely opposite. A superconductor is a material that acquires zero resistance. In other words, it has got infinite conductivity. You put something in there, it comes out the other side. It's infinite conductivity to the flow of charge. So you have charges that are kind of moving about inside of a wire, for example. Superconductors don't stop it in any way, shape, or form. They put up no barriers to that. Most items, in fact, do. Wires heat up, things like that. Energy is lost. But in this case, superconductors can transfer it perfectly. So once electric current is established in a superconductor, the electrons flow indefinitely, right? It's kind of like pushing a car on a road. As long as there's no friction, it's going to keep going, right? That's Newton's first law. That's basically what a superconductor is. Imagine an environment where there's no electrical friction that's going to slow it down. With no electrical resistance, current passes through a superconductor without losing energy. Just the same thing as if you were to take a car and push it, it would actually continue down the road without losing any energy. It would actually conserve that energy. And no heat loss occurs when charges flow. So what we see down here in this picture is copper wire, quite a bit of copper wire actually. And then here we actually see a superconductor, or relatively close to a superconductor. True superconductors are extremely expensive and difficult to acquire, so they usually get the closest thing they can to it. And what the cool thing about these two things is here we see the superconductor, here we see the copper, and basically this is the amount of copper it takes to be able to transmit the same amount of electricity as it takes through these superconductors, right? So this is equal to this in terms of electrical conductivity, in terms of passing electrical current through it. Pretty neat. Another person with their hair standing up, but of course these are great photos for when you're talking about electrostatics. Charged by friction and contact. So for example, stroking cat's fur, or combing your hair, rubbing your shoes on a carpet. We've all done this, and you touched like a wall or something, like, or a doorknob, and you got shocked. What's going on is the electrons transfer from one material to another by simply touching. For example, when a negatively charged rod is placed in contact with a neutral object, some electrons will move to the neutral object. It's just going to happen, right? Electrons are trying to find positive charges anywhere they can. Neutral is better than being stuck with a bunch of other electrons. So it'll actually just go into that area on its own. That gives rise to something called induction. So charging by induction is a common way that we make charged objects. So for example, if you bring a charged object near a conducting surface, electrons are made to move to the surface material, even without physical contact. And remember, I just think that's absolutely fantastic. No physical contact is required, it just does it. So an example, the negative charge at the bottom of a cloud induces a positive charge on the buildings below. So here we got negative charges in the clouds, and look, we're going to get positive charges that are going to start to build up facing the negative here. And you can see why this would set up for an eventual lightning strike. We'll be talking about that shortly. So we can get permanent induction, or permanently induce a charge in something, or relatively permanently do it, by doing kind of a simple procedure. You know, first off, we can consider two spheres. Here we have spheres A and B in 4 different steps. In step A, they touch each other. So in effect, they form a single uncharged conductor. So here we have A and B, they're touching each other. Electrons are able to move around all over A and B. So when a negatively charged rod is brought near A, so here we bring in a negatively charged rod. Look, all the positive charges kind of focus their way towards A. And actually, the better way to think of it is it really is because the positive charges are in the protons or in the nucleus. They're not really moving. What we're really doing is we're driving the negative charges all the way to the farthest side, to B. That's actually a more accurate description of what's going on. So the negative is repelling negative, which yields a positive, right? Doesn't mean that this isn't also still attracted over here, but the negative here is so strong that it's pushing it off to the side. Electrons in the metal, being free to move, are repelled as far as possible until their mutual repulsion is big enough to balance the influence of the rod. The charge is redistributed. In part C, if A and B are separated, while the rod is still present, each will be equal and oppositely charged. So go ahead and pull them apart. While the rod is still there, they'll maintain the charge. And then, of course, you take the rod away, and then you wind up with an entire sphere that's positively charged and another one that is negatively charged. And why did this happen? Because of the flow of electrons. The flow of electrons moved from A to B, and they got stuck in B after the separation. We can also get charge polarization in atoms. So we don't have to just have it on a big level. You know, we're talking about metal spheres. We can actually see this occur on the atomic level. So one side of an atom or molecule is inducing becoming more negative than the opposite side. This is atom or molecule said to be electrically polarized. An electron buzzing around the atomic nucleus produces an electron cloud, right? Remember, I was using the word orbital rather than orbit because it actually fits more closely our idea of how electrons actually move around the proton. It's a very complicated process, and unfortunately it's not going to be covered in the scope of this class, but it is very interesting. There is actually a discussion about it in the textbook that I typically assign for this course, so you can read up on it. The center of the negative cloud normally coincides with the center of the positive nucleus of an atom. So here we have the positive nucleus, and around is usually a big electron cloud. So there's an electron, and it's all over the place all the time around this thing. It basically forms a sphere around it. It's usually a single electron that's doing this, but it's going at such a high speed that we can just describe it as a shell. When an external negative charge is brought nearby to the right, So we bring in a negative charge to the right. The electron cloud is distorted so that the centers of the negative and positive charge no longer coincide. The atom is now electrically polarized. So if I bring in a negative charge over here, and that's going to push this entire cloud over off to the left. Okay, so we've been talking about this somewhat, but let's go ahead and kind of lock in what's been going on, even on an atomic level, right? We've been talking about it with the spheres. We conceptually talked about it on the atomic level. This is what's going on. So if the charged rod is negative, then the positive part of the atom or molecule is tugged in a direction towards the rod, and the negative side of the atom or molecule is pushed in a direction away from the rod. The positive and negative parts of the atom and molecules become aligned. They are electrically polarized. So instead of showing, of course, the example I put up here, I've actually found some clip art showing the exact opposite. So in this case, we have a positively charged one. And what's it going to do? It's basically going to pull or polarize all the atoms in the substance right here, so the negative moves towards the rod, and the positive charge remains on the opposite side. So it winds up being polarized. We see this also with combs, right? We've all brushed our hair, our hair stands up. So we can then take that comb. So when a charged comb is brought nearby, molecules of the paper are also polarized. So here we've got a charged comb. I've been brushing my hair or combing my hair. Winds up having a positive charge. And look, I get a charge induction within the paper as well. So I got the negatives on one side and I have the positives on the opposite side. And that's going to create an electrostatic force. Right? You got a negative charge, force. Positive charge, repelling force. So the sign of the charge closest to the comb is opposite to the comb's charge. Right? And so that means they're going to be, if you remember what we talked about in Coulomb's law, if they have a negative charge, a negative sign on the force, it means it's being attracted. So charges of the same sign are slightly more distant. Closeness wins, and the bits of paper experiencing net attraction. In other words, F here is larger than F here because of the distance. Remember, inverse square law is really important. Okay, charge polarization. We've actually talked about this very example earlier, so we're just going to briefly gloss over it. But again, here's the balloon. We've created negative charges, we've stuck it to the wall, and that's induced positive charges on one side, negative charges, and as a consequence, the balloon sticks to the wall. Many molecules, it turns out, are electrically polarized all the time. You actually don't need to bring in a rod or something like that. Water is a typical polarized molecule. So the distribution of electric charge is not perfectly even in this molecule, even when it's not being induced. So there's a little more negative charge on one side of the molecule than the other. In this case, the electron, this is water, H2O, so here's the O, oxygen, hydrogens on these sides. Now, we show that the hydrogens are the same size as the oxygens. That's actually untrue. Hydrogen is a much smaller atom. In terms of its mass, and also in terms of its influence over the overall molecule. Predominantly, the big sister in that whole thing is the oxygen, and it exerts a much larger influence. And as a consequence of its very large nucleus relative to the hydrogens, it can steal the hydrogen's electrons, which they only have one, to itself. And so as a consequence, the oxygen winds up having more electrical residence time. In other words, the electrons spend more time around the oxygen than they do covalently being shared with the hydrogens over here. So the hydrogens are a little starved, whereas the oxygen is a little flush with electrons. And that creates something called an electric dipole. Such molecules are said to be electric dipoles. So dipole meaning two poles, right? It's charged, it's polarized. Here's a negative pole on this side. Here's a positive, this is a positive pole actually on this side, and this is a negative pole because the electrons are here more and less here. So we've been talking a lot about the actual masses and their charge, but we haven't really talked about how that charge spreads out into open space, right? And that requires some discussion of something called an electric field. We're not going to get real deep into an electric field, but you should know what they are. They're extremely important, and as we go into future chapters, we're going to build on the concept of an electric field and how it's related to magnetics, electromagnetic force, and power production, all kinds of things. So it's important to understand what an electric field is. So an electric field is basically the space surrounding an electric charge. And the textbook I like to use calls it an energetic aura. Basically, these things they manifest themselves into space. Right? The Coulomb's law says that there's no limit. If we go back to Coulomb's law, I'm going to go back to it real quick. Oh, I passed it. Here it is. Coulomb's law says the influence or the force between two charges here is inversely proportional to R. So R, is there any upper limit to how large the radius can be? No. The radius can go all the way up to infinity, actually, and there will still be an electromagnetic force or an electrostatic force. So we can see that the influence is quite large over very, very long distances. Okay, so how big is an electric field? For every object or for every atom, it actually extends all the way to the edge of the universe. Okay, so you might say, why aren't we all attracted to one another? It's because we're offsetting all these charges with other local charges of the opposite sign. So if you have a positive and a negative close by, they cancel each other out typically, and therefore you don't actually see these big force fields that extend all the way out. At least having a massive influence, you don't see it. But there is in fact an electrostatic or an attraction between you and objects very far away. We just simply don't feel the effects of that because it's counterbalanced by other charges. It describes something called an electric force. It's around a charged particle, obeys the inverse square law. We just talked about this. And this is, the units of it is something called force per unit charge. It's kind of like acceleration in gravity is how the electric field works. It's kind of hard to kind of explain without getting into some very basic mathematics, but we're actually going to try to avoid doing that in this course and just speak about it generally. Okay, so the electric field direction is the same direction as the force on a positive charge. So here we have a positive nucleus. In this case, let's say it's a proton. Proton has a positive Q charge. Remember, Q is the charge of an elementary particle like a proton or an electron. And we'll see that the field lines are actually moving away, right? So if I put a positive charge anywhere in this field, it's going to repel it away in that direction, in any direction of these arrows, or in between, you kind of get the idea. If I was to put a positive charge in this field, it would actually attract it, right back down to the negative Q value at the center. So opposite direction to the force of an electron. So this would be the charge of an electron here. Here's a case where we see a person, her name is Lillian. This is out of my book that I like to use. She's touching a Van der Graaf machine. And notice that she is charged. The Van der Graaf machine is actually producing the charge, but the electrons are standing up all around, making her hair stand up everywhere we see here. So we can actually see that her hair is actually defining the electric field, just like this, right? Pushing things away. Back to this, which gives rise to the fact that if we have an electric field, just like a gravity field, then just like we had a gravity potential, MGH, gravitational potential energy, it means we also have electrical potential energy. And that's kind of neat. So this is analogous to gravitational potential energy, energy possessed by a charged particle due to its location in an electric field. So remember under gravity, gravity is kind of the one we already know. We can apply that here to electrostatics here. So here we see there's a rope, we crank it up, and as we lift this block up over this pulley, we're increasing the potential energy, right? According to MGH, mass times gravity times height. And then, of course, if we cut this, the rope breaks, it's converted into kinetic energy. Well, imagine that we have a positive charge attached to a rope on a pulley too, and we have a stationary negative charge. And as we crank that thing up, it pulls itself away. It also is strongly attracted, just like this is attracted through gravity. This is attracted through charge. What's going to happen? you know, if I cut this, it's going to fall. So the potential energy will convert into kinetic energy. So we actually recognize that it's really the same principle, just in a different kind of system. We're just not used to thinking in terms of charges having potential energy, but they do, just like gravitational potential energy. We also see this as manifested in, say, Hooke's law. Hooke's law, remember, was force equals some value k. This is not the same k, by the way, that we see in Coulomb's law. Hooke's law, the value k is the spring constant times the magnitude of the distance, so kx. If you don't remember this, we actually covered this probably about 10 videos ago. But definitely, if you have any questions, send me an email about it. The spring has much more mechanical potential energy when compressed. So if I take a spring under Hooke's law, if I push it in, I'm exerting a force, right? And remember, force is related to energy in this way. The charged particle similarly has an electric potential energy when pushed closer to the charged sphere, just like a spring. So if I have a positive charge here and I bring it closer to a big sphere of positive charges, I have to put a force on it. I have to apply a force to make that happen, because there's a force, remember, electrostatic force that is repelling these two things. I have to apply a force. And if I let go of this positive charge, it's going to zip right back at some velocity. It's actually going to zip back at some acceleration. And that, by the way, defines a force and requires energy to do this, or a transfer of energy, I should say. So electric potential, it turns out, is something called voltage. We hear about it all the time. I guess we don't really think of it as being the same thing as the kind of energy that we see coming out of gravity, but it is analogous to it for sure. And so voltage is energy per charge possessed by a charged particle due to its location. So if you have something with a large amount of electric potential, it's got a higher voltage. If it's got a very small motion in those two charges, you know, in the analogy of gravity, it would be, again, a low voltage. So by comparison with the previous example. So you get the idea. It may be called voltage, which is the potential energy per charge. In equation form, basically, voltage is the electric potential energy divided by the amount of charge. And the unit of measurement is called volt. And that's, if we remember what electric potential energy is, remember potential energy, all energy, whether it be kinetic or potential, is measured in joules, so that's J. And the amount of charge is just coulombs, right? Remember, coulombs is the charge. So for example, let's talk about what this means. So we have twice the charge in same location, has twice the electric potential energy, but the same electric potential, right? Why? Because we've got twice the potential energy. So we've got 2J and twice the charge, 2C. But the voltage isn't going to change because you can just cancel out the 2's. The 2J over 2C is the same thing as J over C. It doesn't change. 3 times the charge in the same location has 3 times the electric potential energy, but the same electric potential, right? In this case, it would be 3J over 3C. You get the idea. So you can have a large amount of energy and a large amount of charge, and the voltage still not change, right? Which leads to some kind of strange things. For example, when you look at a balloon, the kind that we were talking about sticking it to the wall earlier, it's not atypical for those things to get up to 5,000 volts, right? So high voltage can occur at low energy potential, or at low electric potential energy for a small amount of charge. So as long as you don't have a lot of charge, you can get really large voltages, right? It's pretty easy to do that. Or high voltage at a high electric potential energy occurs for lots of charge. So you can get high voltage at high electric potential energy for lots of charge. So as long as you've got a large amount of charge and you have an even larger amount of electric potential energy, you get high voltage. So the difference between the balloon and, say, a high voltage power line is, of course, the amount of charge that's on the system, as well as the amount of potential energy on the system, right? So you don't want to go and grabbing a balloon is not going to hurt you. Grabbing a power line will kill you if you do it in the wrong spot. So how do we store this stuff, right? We talked about how we can induce different things. It turns out there are different ways of doing it, but the way we're going to talk about it right now is through something called a capacitor. Capacitor is kind of a blanket term. It's kind of a neat little word. It's pretty sciencey, but it's really a cool apparatus. So electrical energy can be stored in a common device called a capacitor. And capacitors have been around for a long time. The simplest capacitor is a pair of conducting plates separated by a small distance but not touching each other. As a matter of fact, the closer you can get these things to one another, the stronger the potential for energy storage, right? So these two plates are strongly attracted. You're just not allowed to let them touch or discharge into one another. When the plates are connected to a charging device, such as a battery, electrons are transferred from one plate to the other. This occurs in terms of how we design these things. This occurs as the positive battery terminal pulls electrons. Remember, the positive is pulling the electrons from the plate connected to it. These electrons, in effect, are pumped through the battery and through the negative terminal to the opposite plate. The capacitor plates then have equal and opposite charges. The positive plate connected to the positive battery terminal and the negative plate connected to the negative terminal. So how do we see the capacitors are normally used in, say, computers or in almost any electrical device? Well, instead of doing them as nice flat plates, to save space, we usually actually roll them up. You see two separate plates here. We put something called a metal, there's a metal plate here, here's another metal plate, maybe some aluminum around the outside, but then we roll it up and we have the negative charge connection and the positive charge connection. It's all insulated all around. And basically we can put a lot of electrical power as long as these plates don't touch, right? As long as they don't touch. We could make sure that we could put a lot of what they call a dielectric in between, something that the electrical charges can't go across, like paper. As long as they're separated, you can put a lot of charge into these capacitors and store it. And so actually this is kind of a neat one because this is kind of a primitive capacitor that people have done experiments with. You can actually generate a charge on one side or the other, and you actually watch, as long as there's air here, you can actually get sparks to move across here. So the charging process is complete when the potential difference between the plates equals the potential difference between the battery terminals, which is to say the voltage. So we come back over here, we turn these things on. What's happening is it's basically going to start creating the difference when we've got the battery on through the system. The greater the battery voltage and the larger and closer the plates, the greater the charge that can be stored, right? So the greater the voltage, closer the plates, and of course if you got big plates, that also helps. The energy stored in a capacitor comes from the work required to charge it. So work is coming in. Remember, work is also a unit given in joules as well. Discharging a charged capacitor can be a shocking experience if you happen to be, in the conducting path. There have been many people that have been shocked by capacitors. Capacitors are used in many different appliances, or things that we use all the time. For example, televisions. It's used in certain kinds of electrical devices in automobiles, radios, you name it. So you have to be careful. If you take say a television and you throw it in your backyard and you happen to be goofing off with it, and there's a charged capacitor still in it, it can zap you. It can stop your heart pretty easily. So you have to be really careful with things like television sets, microwaves, things like this. All right. Well, I mean, that kind of takes us through our whole world of electrostatics. It's a lot to kind of take in, but we're going to build on this. It's not something that a lot of people are accustomed to thinking about. But a lot of it, if you think about gravity and if you think about how water moves through, say, a water pipe system or something like this, suddenly things will start to make sense, especially as we move into the next lecture when we talk about electric currents and circuits. So with that said, I hope that you enjoyed this lecture. If you have any questions, send me an email or meet me on the discussion boards. Until next time, I really hope that you have a good one. Bye.